Hi, this is Ken Willis of Cadence Design Systems. Welcome to Sigerty Tech Tips. Today we bring you another installment of how to sign off your design using a power-aware signal integrity methodology. Our video today will show you how signal integrity engineers can overcome the challenge of extracting large S parameters for their memory interfaces, which may not simulate effectively in their circuit simulator. Successfully implementing memory interfaces, such as DDR4, is one of the most challenging tasks faced by SI engineers. Early in the design process, memory interfaces are typically analyzed using ideal power so that first-order signal integrity and crosstalk problems can be assessed and corrected. However, significant challenges are faced by SI engineers during the sign-off stage when power-aware signal integrity analysis is performed to assess the effect of simultaneous switching noise, or SSN. To evaluate SSN, interconnect models must include signal, power, and ground structures, as well as the coupling between them. Hybrid or full-wave 3D field solvers are often used to extract S-parameter models for the parasitics of the PCB. Unfortunately, S-parameters for large DDR data buses may not simulate well in many circuit simulators, resulting in convergence or stability issues in the results. To help address this, a conversion process to a simpler broadband SPICE model can be performed. But this conversion often requires modification to the model for passivity and causality, which can leave the SI engineer wondering about the accuracy of their SSN simulation. With Sigerty, SI engineers have an alternative method. Our FDTD direct simulation methodology calls our unique hybrid solver in combination with our finite difference time domain, or FDTD engine, which solves PCB and package geometries directly and performs power-aware SI analysis in the time domain without S-parameter. Signal integrity engineers can confidently and accurately perform their detailed SI analysis, including SSN effects, without having to process large, complex S-parameters. With SSN simulation results captured accurately and simulating cleanly, SI engineers will have high confidence when they sign off on the memory interface that the simulation results will match the results measured in the lab. This helps reduce design respins and gets product to market on time. The results may be higher market share, and who knows, maybe even a nice end-of-the-year bonus for your product development team. In today's video, you will see us utilize the Allegro Sigerty SI Base and power-aware SI option. To learn more about these products, visit us at www.cadence.com. Now I will turn it over to my colleague, Jen Mu.
Thanks, Ken. I'd like to use this opportunity to discuss the new function in Cadence Sigerty 2016 release, the FDTD method with layout association at system level. The picture here illustrates team workflow. Extract PCB model from physical layout, assign the model to a block, complete all block creation and assignment, run time domain simulation using SPICE-like simulator to generate waveforms for post-process, but it doesn't allow direct access to the layout environment. If designers want to make changes to the layout and resimulate, they have to go back to the layout, change it, and do the model extraction and assignment again. For power-aware simulations, the extracted models are often in S-parameter format with a large number of ports. It may require broadband SPICE circuit model conversion to avoid convergence problem during simulation. In the new release of System SI, we added in a new flow. For simulations with non-ideal power supply, instead of extracting a model from a layout, we link a block in System SI to a board or package directly. That there is no model extraction anymore, and the simulator is not SPICE-like, but FDTD based. It gives users the advantages of both environments, physical layout and system simulation, plus the FDTD-based simulator to take into account of any power and signal interaction. At the system level, we directly open a physical layout and set up signals, decoupling capacitors and simulations, then enable the FDTD-based simulator from System SI. After the simulation completes, The result will be processed and reported in the same way as if using extracted models. With this flow, users don't need to extract models beforehand. That will help avoid certain convergence problems associated with SPICE-like simulators. More importantly, it's easy for users to perform what-if analysis by modifying the physical layout during system-level analysis. In System SI, open parallel bus analysis workflow. We can set up controllers, memories, and power supply, then add other interconnect parts. Now, let me show you the new FDTT simulator-based flow. We have a new block for directly run power-aware simulation from System SI. Using this block, we set the name, select board file, and inform the tool we will use the FDTT-based simulator later. Then we open Speed 2000 to select signals. This time, the layout association workflow is used. We select signal net, specify mesh, and obtain connection information between devices and signals. After save all the setup, quit from Speed 2000. The connection mapping information is displayed here in System SI. Now, we again make connections between the PCB model and devices models. We will set up simulation parameters and models as we did with SPICE model extraction. When we start simulation, the tool calls FDTT simulator in background. The results of the simulation have non-ideal power effect. In summary, this movie shows the new simulation flow in System SI using FDTT-based simulator. It helps designers perform what-if analysis at system level for high-speed memory bus and serial link analysis.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.